This is Geometry, Section 2.1, Inductive Reasoning. So there are two types of reasoning used in geometry. We use inductive reasoning, which we'll learn about today, and we also use deductive reasoning, which we will learn about later this chapter. So inductive reasoning is basically noticing a pattern and making a guess. So, for example, if we look at this pattern right here, we're adding up odd integers in order. So, to start off with, 1 equals itself 1, 1 plus 3 equals 4, 1 plus 3 plus 5 would equal 9, 1 plus 3 plus 5, so that was 9, plus 7 would equal 16, that plus 9 would equal 25, and that plus 11 would equal 36. So, based on this pattern, we want to guess a conclusion. So here we were adding up odd integers, so our conclusion would be that the sum of the first n, so we're just going to use n as a number, so any number of odd integers. If we look at what's happening here, these are all something that we call perfect squares. So 1 squared is 1, 2 squared is 2, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So the pattern here is that the sum of the first n odd integers, so if I add up odd integers one after another, I'm always going to get a perfect square. So it would be the sum of the first n odd integers is whatever n is squared. So if I add up the first one, I get 1 squared. So n being 1, I would get 1 squared, which is 1. N being 2, so 2 odd integers, I would get 2 squared, which is 4, and so on and so forth. So if I were to guess this, I would first have to figure out how many odd integers am I adding up here. So this is just this pattern up here continued, and I want to guess what the number is going to be based on my conclusion right here. So 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, and then I would have 21 and 23. So I have to count up how many that is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. So based on my guess up here, I should get 12 squared, which is 144. And that actually is true. If I add up all of these numbers, that pattern holds, and I do get 144. So, second example, if I let x be 1, 2, 3, and 4, and I figure out 8x for all of those numbers, as well as x squared for all of those numbers. So, 8 times 1 would be 8, 8 times 2 would be 16, 8 times 3, 24, 8 times 4, 32. X squared, so 1 squared is 1, 2 squared, 4, 3 squared, 9, 4 squared, 16. So, guess a conclusion based on this. So the only thing I can really notice about this is that this number is always bigger than this number. So if I multiply a number by 8, I'm going to get a greater number than if I square it. That's the only thing I can really notice from this pattern. So my guess is going to be that 8x, 8 times some number, is going to be greater than whatever that number is squared. However, this is an invalid conclusion, because if I continue this pattern, I keep doing 5, 6, 7, 8, so on and so forth, once I get to 9, 8 times 9 is not going to be greater than 9 squared, because 8 times 9 is 72, and 9 squared is 81. 72 is not greater than 81, so this conclusion does not hold. So when we do this, when we make a guess based on a pattern, we call that a conjecture. Conjecture is just an educated guess. Sometimes, however, like we saw up here with this example, sometimes our conjecture is proved wrong. So an example that proves a conjecture wrong is called a counterexample. So what do I mean by that? So an example, June and July are both start with J and are both in the summer. So this is a pattern here. June and July both start with J, both are in the summer. So conjecture, I can make a conjecture about this pattern. So I'm going to say, all right, well, based on this, I'm going to say that all months that start with J are in the summer. However, we know that that's not true because our counterexample to this conjecture would be that January is a month starting with J, but January is in the winter. So my conjecture is wrong because my conjecture said all months that start with J are in the summer. Well, January is a month that starts with J, but January is not in the summer, so this would be my counterexample. So, more with counterexamples. First one says the product of two positive numbers is greater than either number. So, we want to try to write a counterexample for this. To start, we're going to write a statement that describes our counterexample. So, we want to find two positive numbers with a product less than either number, because my conjecture says that the product of two positive numbers is always greater than either number. So, if I take two numbers that are smaller than 1, if I take 0.5 times 0.4, if I multiply those two numbers together, I get 0.2. Well, let's go back to my original conjecture. The original conjecture said the product of two positive numbers, so 0.5 and 0.4 are two positive numbers. It says that the product of those two numbers is going to be greater than either of those two numbers. Well, 0.2 is not bigger than 0.4, and it's not bigger than 0.5, so this is a counterexample. It proved our conjecture is false. Second one, the difference of two integers is less than either integer. Well, think about negative numbers. So if I pick 5 and negative 6, it says the difference of these two integers should be less than either of those numbers. Well, if I subtract a negative 6 from 5, that's really the same as adding 6 to 5, and I get 11. However, it says the difference of these two integers should be less than either integer. 11 is greater than both of these numbers, so this is false. This is my counterexample. Find a pattern for each sequence. Use the pattern to show the next two terms of the sequence. So I've got this sequence of numbers here. So to get from 2 to 3, I add 1. To get from 3 to 5, I add 2. To get from 5 to 7, I also add 2. To get from 7 to 11, I add 4. To get from 11 to 13, I add 2. So this is kind of a weird pattern here. First I'm adding 1, then 2, then 2, then 4. So it looks like it's going up, but then after 4 I go back to 2. So maybe this pattern is just a mirror of itself. I go 1, 2, 2, 4, and then back the other way. So 2, 2, 1, plus 2, plus 2, plus 1. So if I follow that pattern, the next two terms of my sequence would be 13 plus 2, or 15, and then 15 plus 1, or 16. Next one, so this one I start with just one square, then I add another square on the other side of it, then I add one to the top, then I fill in this right here. So if I follow that pattern, I've got one square here. So now this was my figure, so first thing I did was add a square to this side. Then so I've got this figure, then I added a square to the top. So these two figures would be following that pattern that we have here. Next, use the sequence and inductive reasoning, which we've been talking about, to make a conjecture. So what is the 12th figure in the sequence? Instead of drawing out 12 figures, we're just going to make a conjecture, make a guess about what that 12th figure would be based on the pattern that we notice. So this is kind of like a clock. It starts at 12 o'clock, moves to 3 o'clock, 6 o'clock, 9 o'clock. We could probably guess that the next one would be back at 12 o'clock. So if we want to figure out the 12th figure in the sequence, we could just count 12 spots all the way around, going a quarter of the way around the circle each time. So this is the first one. Second one would be here. Third one, fourth one, fifth one, 6, 7, 8, 9, 10, 11, 12 would end up at this spot right here. So the 12th figure would most likely look like that if it follows the pattern that we noticed. Next one, what are the coordinates of the point in the 8th figure in the sequence? So we've got 3 figures here. We want to guess what the 8th figure would look like. So first we start down here, 2, -5. Then we jump up here to +2, +5. Then we jump over here, -2 to 5. So really we're reflecting this point across the x-axis, then across the y-axis. So probably the next one would be reflect across the x-axis, then across the y-axis to end up back at this spot where we started, just like this clock example up here. So I want to figure out the 8th one. So I start here, then I move here. That's 2, 3, 4, 5, 6, 7, 8 would most likely be here. So we've got to figure out what are the coordinates of that. So if I'm in this quadrant, the x-coordinate would be negative since it's over here, and the y-coordinate would also be negative since it's over here, so my point would be -2, -5. Make a conjecture for the scenario. So I want to make a conjecture for the sum of the first 100 even numbers. So the first example that we did was adding up odd integers. Now I want to add up the first 100 even numbers. So I start with 2. 2 is an even number. It's the first one. 2 equals itself 2. We'll come back to this column over here. 2 plus 4, so the first 2 even numbers, equals 6. 2 plus 4 plus 6 equals this plus 6, so 12. 2 plus 4 plus 6 was 12, plus the next even number is 8. That equals 20. So now notice a pattern about these things. So we've got 2, 6, 12, and 20. Those numbers can also be found by multiplying numbers together in a pattern. So 2 is 1 times 2. 6 is 2 times 3. 12 is 3 times 4. So notice that we're multiplying sequential numbers, and then we're bringing this number down here. So this should be 4 times 5, which is 20. So how do I figure out the first 100 even numbers? Well, this was 1 even number. This was 2 even numbers. This was 3. This was 4. I want 100. So the first 1 even number was 1 times 2. So 1 times the next number. 2 was itself 2 times the next number. 3 was 3 itself times the next number. So 100 should be 100 itself times the number after it, 101. 100 times 101 gives us 10,100, which actually is what you get if you took the time to add up 2 plus 4 plus 6 plus 8 all the way. 100 even numbers would take you all the way to 200. That would take a very long time to add up, so we use this pattern that we found to do it a lot more quickly.